Hello. A quick video along with some slides. Excuse me. Energy types and energy conservation. With these slides, I'm hoping you will use this sheet that is included in the assignment stuff today. You can go through and write some of these things down, and we'll go from there. All right. Okay. So, energy is one of these things. It's tough to define. So sometimes with things that are unusual or have real technical definitions, instead of giving it a great definition, we often talk about it being what it does. So, like, energy is what it does. When we talk about what money is, if somebody says, "Hey, define money," it's kind of tough to do that. What's a dollar? Well, it's 100 pennies. Well, okay, what's 100 pennies? 4 quarters. What's 4 quarters? And we get to something at some point where somebody might end up saying, well, money is something that you can trade for other things. And we're talking about what money does as what it is. And so I'm going to talk about energy in that same way. So we'll say that energy is something that if energy is transferred, we see a change in speed, or an object change the height or the location of a system, the height of the object. We can see a change in temperature of the system. Energy must have been transferred. If a system or an object bends or changes shape, there must have been energy transferred. If something gets more or less bright, there must be energy transferred. If a chemical reaction happens, then we usually see some combination of these things. Energy must have been transferred. So those are all signs that there's a transfer of energy present. One of the first types of energy that we'll talk about here are kinetic energy. I better move this bugger. So, kinetic energy is what we often talk about as moving energy. So, with kinetic energy or moving energy, it depends on a few things. It depends on the mass of the object, and it depends on the velocity of the object. Those are the things that it really depends on. We have evidence that there is kinetic energy if we are looking at a scenario and we're trying to determine if kinetic energy is present. Well, the object must have a velocity that's not zero. It must be. We generally, when we do that, we have to compare it to something that's stationary. We have to, if a car drives by, we can say it's going 30 miles an hour. We would be comparing that 30 miles an hour to like a tree on the side of the road or the ground or something like that. Something that we say is stationary or we assume is stationary. Big picture sort of things. Yeah, the Earth is rotating and revolving around the sun, and the whole galaxy is moving. But at some point, we have to say, hey, for what we're doing right here, I'm going to say the Earth, the ground, the road, the tree are stationary. So if we see an object that is moving compared to some reference frame, then that object is moving. It must have kinetic energy. The equation for kinetic energy, and we saw this in one of our Google Forms earlier, the equation for kinetic energy is 1/2 times the mass times the velocity squared. Now, where this equation comes from is really a bunch of experimentation. So scientists back in the day and throughout time run a bunch of experiments. They collect data, they plot graphs out, they see what happens here, what happens there. And this equation is really the result of a bunch of experimentation. It's possible to do that experimentation at the high school level. It's time consuming, and with the distance learning stuff, we're just going to say for now, hey, this is what we got. You can see right here that I'm using EK to represent kinetic energy. In an equation, I try to stick with E for energy and then little subscript notes for which kind of energy. Energy, which kind? Kinetic. Some people also will just say KE. That's fairly common. Units of measure. Kinetic energy could be measured in Newton meters. That's a Newton times a meter. A real intro level thing, a real common intro level challenge is to avoid saying Newtons per meter because it's not a per. Per implies division. So it's a Newton meter. And a Newton meter is the same thing as a joule. which can be simplified as a capital J. Kinetic energy is measured in joules or Newton meters. All energy measured in joules or Newton meters. Now, there are different systems that can use different things to measure energy. So this is the metric system that measures energy in joules. The old British standard system is calories. So like when we talk about food calories, we're talking about forms of energy. So that's kinetic energy. Bada bing, bada boom. Gravitational potential energy. In the past, it's really common for people just to call this potential energy, and there are a bunch of different types of stored energy. I think it's in my preference. I try to say gravitational energy or gravitational potential energy. Just saying potential is a bit on the sketchy side. It can leave a little bit too much mystery. So gravitational energy, gravitational potential energy, depends on the mass of an object, how high it is compared to some reference point. For us, oftentimes just the ground. And it depends on the gravitational field of the Earth. We did that G, the gravitational field of the Earth, in the last unit when we were talking about weight, or the force due to gravity, the gravitational force of the Earth on something. So the gravitational field G is 9.8 newtons per kilogram. The other thing that we must have when we talk about our system, we'll talk about all these different things that interact. For there to be gravitational energy or gravitational potential energy, the Earth and the other object must both be in our system. If we've only got one of those two, there's not gravitational energy. We then talk about it or describe that energy in a different way. Oops, wrong way. I just stuck that 9.8 value in down there. Evidence. So if we're looking at a question and we want to see exactly what's going on, or if we're looking at a situation or scenario, we want to know if gravitational energy is present. If there's an object there, well, it must have mass. We're good. That's the first step. Second thing, the object must have a height that's greater than 0, our reference point. Then the last thing, it has to be on Earth for G to be 9.8. If it's not on Earth, it would have to be in some other location where there's a gravitational field. It'd have to be on some other planet or something like that. If something is out in space, there are still gravitational energies, but it involves a very different equation to calculate that. And that's something we're not going to go into. So for us, if we're looking for evidence that a question that we are working on, or a scenario or a lab situation has gravitational energy, we would say it pretty much has to be on Earth or another planet, mainly on Earth, and that the height has to be greater than 0. The equation for gravitational energy, energy, which kind? Gravitational. Glad you asked. Gravitational energy is mass times G, and G is the gravitational field of the Earth. So mass times G times the height. And again, remembering G is that 9.8 newtons per kilogram. There are two common ways at this grade level that we would see gravitational energy written out, or as symbols for it. E with that little subscript G. Sometimes we'll just see GPE for gravitational potential energy. There are, in some places, in more advanced texts, they'll use the letter U for all sorts of potentials, and then they'll say there's U for gravitational, U for potential energy, and then they would somehow use a set of subscripts possibly to imitate to convey that the potential energy was gravitational. These are the two that we will use. I try to stick with this EG sort of a thing. And then again, units of measure, all energy, gravitational, kinetic, any sort of energy in the metric system is measured in joules. Another form of energy, elastic energy. Elastic energy depends on how much an object stretches. So it does require then some sort of a stretchy object, like a spring or a rubber band, bungee cords, something stretchy. So that's how much that thing stretches, and I suppose also then how stretchy that object is. Not I suppose, definitely. but we generally won't worry about that. We will generally worry about how much the object stretches. So if we're looking at a situation and we're trying to figure out if there is elastic energy, our evidence is that not only is there a stretchy thing there, but that stretchy thing is stretched. If you have a bungee cord but it's not stretched, it's just sitting there laying on the ground, well, there's no elastic energy there. There's the possibility in the future that you might have some, but there isn't any now. So if there's elastic energy, that stretchy thing has to be stretched. It has to be uncomfortable, either stretched. It is also possible to have elastic energy if something's compressed, right? If you have a spring that you squeeze in. So either of those things, if it's stretched or compressed, or if it's a stretchy thing that's uncomfortable, then there is elastic energy. There are definitely ways to calculate elastic energy just based on how stretchy the object is. It's called like a spring constant is a common way to call that. And by how far that the object has stretched, it's how long it is compared to its equilibrium position or its rest position. But that's one of the things that we're not going to do in this course. We're not going to do everything. We have to limit some things. So we're not going to do those equations or those calculations. The symbol in equations for us, we're going to say energy, what kind? Elastic. There you go. And then again, all energy measured in joules. Thermal energy. In some cases, we'll call this dissipated energy as well. Skipping the depends on column since we're not going to do the calculation. Again, there is an equation. There are ways to calculate it, but it's one of the things that we're simplifying here. So evidence for thermal energy. Friction is significant when things slide. That's, you do that sort of a thing and you notice that there's a change in temperature. So friction being present, there's a change in temperature. If you have soapy water on your hands when you do this, you notice the change in temperature is much less than if your hands are dry. The fact that the friction is significant is the thing that causes this change in temperature. That's another indication or evidence that thermal energy is present. If something that was warm is no longer warm, that's a change in temperature, yeah. Sometimes we think of change in temperatures as something getting warmer, but if something gets colder, there's also thermal energy that was present and it just changed where that thermal energy is concentrated. So any of those sorts of things are indications or evidence that thermal energy is a significant player in a problem. In equations, we are going to go with E with the subscript T for thermal, or we're going to go with E with a subscript D or dis for dissipated. So a quick note on the dissipated energy, that's this sort of a thing. So if I do this, my hands are warm, and then when I stop, my hands cool down fairly quickly. The energy that was made this temperature change, that energy is still present, but it leaves my hands and it goes to the surrounding air and the rest of the room and all of those sorts of things. That energy is still present. It's just not here anymore. It's spread out into other spots, kind of like it's gotten diluted in the room, right? If you have a candle or a fireplace and there's heat, there's flame right there, right? Well, if it's a fireplace, that energy that doesn't just stay in the fireplace, it spreads out throughout the room, throughout the house, throughout the region that you're in, and that energy doesn't go away. It just kind of moves locations and it gets spread out throughout the region that you're in. So that getting spread out is where we talk about it being dissipated. So that's another way to think about some of these things. If thermal energy is concentrated in a spot, it's just talking about thermal energy. Other people will say, well, that energy spreads out. Another way to look at it, not necessarily a right or wrong way. Another way to look at it, though, is to say that if energy was there and it goes away, that energy is dissipated. And again, all energy measured in joules. Chemical energy depends on a variety of things. The chemicals that we have, bonds present, all sorts of different things. We're not going to worry about that here. There are, again, definitely ways to calculate it. Chemistry that uses that. So, but the evidence that a chemical that we're going to be concerned about chemical energy. Chemical energy is a thing if a chemical reaction has taken place. In the examples that we use in this course, if there's fire, well, there's chemical energy. If there's a person that ends up pushing or pulling or doing stuff to a system or included within a system, we get our energy from the food we eat. And when we digest that food, and that food gives us energy through a chemical process. It's chemical reactions that take place within our body that give us that food. In the U.S., if you have a food container, it talks about the energy of these different things in calories. In Canada, some, maybe not all, I'm not sure, but I've definitely seen in Canada, some little food containers will mention the energy content of a bag of chips or whatever, not in joules, but or pardon me, not in calories, but in joules. So the little bag of chips would say how many ever joules of energy it has. Kind of a neat thing. Again, there are ways to calculate it. There are equations for it. We are not going to use them in this class. We have to limit some things. The symbol for this in equations for us, we're going to say E for energy, subscript C for chemical. Now, when we talk about systems, we've done system schemas for free body diagrams and forces. They continue to be a useful thing here. So if we have a closed system, what we're saying then is that if we draw our system schema and everything or whatever is our system, a system is closed if no other objects can interact with the system. No object can enter into our system and putz with stuff. None of our system leaves the system and putzes with other things outside of our system. Everything is inside. That's it. Nothing else. No other things go in or out of our system. That's a closed system. An isolated system means that energy cannot enter or leave the system. It's a little subtle difference between these two. If it's an isolated system, not only can objects not enter or leave, but we would say that if there's a fire, right? We're looking at chemical energy. We would say that it's an insulated system so that none of that thermal energy can leave the system. Maybe we have it wrapped in some sort of insulation, reflective surfaces, things like that, and we would do our best to make sure that none of that thermal energy could leave our system. That would be an isolated system. In Physics 9, we're going to basically say the quickest way for us to do this closed isolated system in Physics 9 is to say, hey, we're just going to say everything is in our system. If everything is in our system, well, no objects can leave, no energy can enter or leave, we're covered. That's the most common way for us to talk about closed and isolated systems. We will not have one of these be true and the other not for what we're doing. Conservation of energy. So there are multiple definitions or multiple ways to use this phrase. In environmental science, they don't usually talk about conservation of energy. They will talk about energy conservation. And in environmental sciences, energy conservation is saying, hey, we want to save our resources. Turn lights off when you leave the room, or if you don't need them, share or carpool ways to get to different places so you're not burning a bunch of fossil fuels. All of those things are perfectly legitimate environmental science ways to talk about energy conservation. But when we're talking about energy conservation or conservation of energy, when we're talking about that in physics, this is not the definition we would use. It's a perfectly valid definition for environmental sciences and for other areas, but it's not what we mean when we talk about energy conservation or conservation of energy in physics. When we talk about it in physics, we're saying that the total energy in a system cannot be created or destroyed, or energy anywhere cannot be created or destroyed. It can only change to different forms of energy. Einstein actually is one of the folks that came up with a unique way to go about this, that E equals mc squared, that is so well known or easily identified. That is saying that energy and mass have some form of equivalence. So I'm not going to go into that right now, but I just wanted to make sure that we know that energy cannot be created or destroyed. It can change different forms. With nuclear processes, that form is like a mass converting to energy. In nuclear power plants, there's a small bit of, for every molecule that's present that is going through this process, there's a small bit of mass that just gets obliterated. It doesn't turn, no dust, no smoke. That mass is gone. And in its place, energy, which is stinking insane, right? I mean, that's crazy. So we've been lying to you for like 13, 14, 15 years, right? Uh, Mass can be destroyed, but mass energy, one of the two, they're equivalent. Now I'm going into this E equals mc squared thing. Danger. But if mass is destroyed, and this only happens in nuclear reaction type processes, then if that mass is destroyed, it creates energy. So energy and mass are equivalent. When we say energy cannot be created or destroyed, we mean energy and mass cannot be created or destroyed. It can only change to different forms. Now, that doesn't mean we can suddenly change any mass to being not gone. It has to be a specific sort of thing. You've heard about uranium, plutonium, those sorts of things. That's probably where we should leave it. I shouldn't have gotten into it. But conservation of energy in physics, going back, big picture, conservation of energy in physics is saying that we cannot create or destroy energy. We can change it from one form to another. If energy is visible in one form, it is possible for it to be converted to being visible in another form. We can maybe see an object is moving at one point, and then as it's moving, it goes up, right? You throw an object, it goes, right? Well, when it left your hand, it had a lot of kinetic energy because it was going fast. As it goes up, it slows down, slows down, slows down. And at the peak, for an instant, its velocity is zero. It has no kinetic energy. It's changed from having visible kinetic energy to now it has gravitational energy being at this new height. And so it's changed from being visible as kinetic energy to being visible as gravitational energy. And now it comes back down and it speeds up. And at the bottom, its height is zero, so the gravitational energy is zero, and it was all kinetic energy until it hits the ground, right? Then when it hits the ground, well, then there's that impact. Maybe you make a little bit of a dent into the ground. You use some energy to dent the dirt. There's energy that creates that sound. When it hits, there's a little bit of internal friction and stuff. That energy becomes thermal energy. So all of those things are conversions of energy being visible in one form to another. The equation for this conservation of energy deal in physics is we would say that the total initial energy equals the total final energy. And we can go through and do some accounting for all of those things. Instead of just saying total initial and total final, we can go through and use this. God dang, I can't figure out a way to get down here without that little bugger toolbar showing up. So I'm going to leave my mouse up above here for a little bit. So when we talk about total initial energy and total final energy, we'll try to, how close can I get? Total initial energy equals total final energy. Instead of just saying total initial energy, we can say, well, what kinds of energy are there? Well, shoot, I thought that would work. Maybe if I just sit here and wait, yeah, that will go away. So when we talk about the total initial energy, we can list all of the kinds of energy that are present initially. There could be kinetic energy, gravitational energy in the beginning. There could be elastic or thermal energy initially. The sum of all of those in the beginning equals the sum of all of those in the end. Kinetic final plus gravitational energy final plus elastic energy final plus thermal energy final. The sum of all of the big energies in the beginning equals the sum of all of the energies in the end. Now, this is a statement for the conservation of energy in a closed system. Total energy in the beginning equals total energy in the end. There's another way to talk about conservation of energy if our system is open. We'll do that tomorrow. Okay, so I'm going to go through and do then an example of representing energy with bar graphs, LOL graphs. in just a second here. And this example is off of your worksheet for today. You know what? I'm going to actually do this um, on the and put the video for this on the actual worksheet itself. So that's it for this slideshow. This bit of stuff, the bar graph stuff, I'm going to do that like I just said. I'll put that video as a tutorial right on the worksheet there. Have a good one.